I want to talk about state variable dynamics, and in particular, the core state variable dynamics that we typically run into and how we solve and just how we look at this that we would see in a linear state system, sort of a linear state system. Now, normally, the core is looking at the state variable x of t and what happens in terms of a sub t. A sub t, which can be constant or a factor of time. Now, normally there's always an input driving it, and then we look at what is the output as a function of inputs and outputs, but really the key dynamics happens around this set of differential equations. So usually we like to start by always talking about this for a constant matrix A. And you think, well, okay, there's a couple ways to approach that. And in this particular linear time invariant case, we get this nice differential equation. A couple ways to approach this. One is to take A and project it across an eigenvector basis, which that might be E, which has a whole bunch of, which is basically eigenvector rows of A, and where lambda is a diagonal matrix of just all of the ordered eigenvalues, to which then I can take A as a decomposition of E lambda E inverse. Typical structure. If you do that, this differential equation becomes a very reasonable differential equation for x1 and lambda, which basically, because it's a diagonal matrix, means all of these differential equations just fall into x, into simple single state elements that entirely depend on the eigenvalues at each one of these points. And you think, great! So that's one way to solve it. The other way to approach this is to take this structure and realize that I'm actually getting, I can actually solve this by using the matrix exponential form. Feels very much like treating A as a scalar, and at one level it is, and one level not so much. But it does allow us to write it down in this form. I can actually take this formulation and realize that I can break this apart through the eigenvector basis and eventually arrive at exactly the same solutions for in the x1 projection space. So everything makes sense there. So if for a constant A, I have all of the tools probably that you may even be familiar with in different places of how to solve the structure. But this really gives us a very clear way to look at the dynamics and realize that the eigenvalues bring everything to bear. Now you may ask yourself, what would I do if this is actually a function of time? What's the solution? Well, I could imagine many ways to try to go and solve this differential equation depending on what A is and what it's looking like. There's a whole range of theory that if A of t was actually a periodic function, there's a whole set of theory talking about Floquet theory that would actually say, well, what would that look like? That's often, when I'm dealing with state variable systems, not what I'm actually asking. I'm actually asking, are things changing because something about the system has moved away from its linearization point maybe, or something of the sort. There's a whole range of things in this, but we might say, can I come up with an equivalent solution that might allow me to sort of do some levels of expansions when I need it? Okay. So it turns out there is one series that works. It's this Pinot-Baker series, which is basically going, again, looks like 1 plus a first integral plus double integral plus a triple integral. It feels, this is sort of a linear series which is giving me higher and higher powers to handle this. Now what's interesting about it is that this particular series, if I take the derivative of it, it equals to a of t times that function. And you're like, oh, great, that does give me the solution to this. Now, whether I like this series or not, I don't know. It does work. It turns out to be globally stable. This is great. It does allow me to talk about that my solution x of t would then be whatever that particular matrix component is of the initial condition to time times the initial condition. Interestingly enough, I can also, if I say I run the system to T1 and then go from T1 to T, it is the multiplication of those two matrices. This is not surprising because usually you would expect a differential equation to depend primarily on this initial condition. So it's nice that this multiplication property holds. So things basically start on their initial condition. So if I have this as my formulation, I can talk about the solution for a typical, linear system solution where I bring in the inputs, which is usually going to be a U vector, that has some matrix in terms of how it gets modified or how it gets set up, and then also the C and D matrix in terms of how I create the output. I can use this phi to effectively give me a generic general solution form. And at least I have a general solution form that always will work. And so I can build from that. Now, the interesting thing, just as an aside, you say, well, how does this look like if A is constant? This should go back to our conversation here. Interestingly enough, it turns out if all of the A's are there and I work through the integrals, I get the A power because it keeps getting to a higher and higher power, which, by the way, gives you a sense of why I'm doing this. It feels that sort of same sense as a Taylor approximation. And it turns out that not only do I get higher order for time related to its initial condition t0, but it's over k factorial. Interestingly enough, when A of k is fixed, this is a definition of the matrix exponential coming from initial condition. Phew, okay, it all works. It's all consistent. This is great. So this allows us to kind of build on these ideas. It allows me to still have the same solutions for x and x of t, which would be my state variable, and y of t that I would expect that would have these various components. And so everything is consistent. This may not be the integral form you want, because it might be complicated, but at least it's enough that you can start to work with and work and approximate it. And so now this at least gives us at least ground truth to be able to build on this. It gives us a way to say I can solve this, I can look at the dynamics, and now I can kind of build from these points. Whether the system I'm looking at a nonlinear system that I'm bringing this in, or a linear system that has these, or wherever this may be going.